everyone, this is Chinnaiah Kalpana here. In this video, we are going to solve a differential equation from higher order linear differential equations. So let's get going. Problem: solve d cube y by dx cube plus a square dy by dx equals to sine ax. Firstly, let's find the order and degree of the given differential equation. Identify the highest derivative. Here, d cube y by dx cube is the highest derivative, so our order will be 3. And the highest power of the highest derivative is our degree. Degree will be 1. Now coming to the problem, we are given a differential equation. Now we'll write the differential equation in operator form. Given differential equation, d cube y by dx cube plus a square dy by dx equals to sine ax. We know that differential operator d equals to dy dx, the d square is d square by dx square. Then we can write d cube as d cube by dx cube, right? Now we can write the given differential equation as d cube y plus a square dy equals to sine ax. Now let's take d common from the first two terms or two terms of LHS. We'll get d cube plus a square d into y equals to sine ax, which is in operator form. F of d into y equals to q, where f of d equals to d cube plus a square d and q equals to sine ax. Now we need to find the general solution to the given equation, which is given by y equals to yc plus yp. Here yc is a complementary function. We'll get yc using roots of the auxiliary equation of homogeneous equation of the given differential equation or the differential equation in operator form. Okay, so if we equate the RHS to 0, we'll get f of d into y equals to 0, which will be a homogeneous equation of the non-homogeneous equation, right? And we'll find yp using 1 by f of d into q. So firstly, let's find complementary function. The auxiliary equation of, we'll find complementary function using auxiliary equation. The auxiliary equation of f of d into y equals to 0 is f of m equals to 0, where f of m equals to, we have f of d equals to d cube plus a square d, right? We can replace differential operator d by m, so that we'll get f of m equals to m cube plus a square m. Then our auxiliary equation becomes m cube plus a square m equals to 0. Now we need to find roots to the auxiliary equation. Take m common from the two terms, we'll get m times m square plus a square equals to 0. You can equate each factor to 0, okay? From m equals to 0, we'll get one root, which is 0. And from m square plus a square equals to 0, we'll get two roots. We can find roots using two ways, okay? From this m square plus a square equals to 0. Then m equals to plus or minus square root of minus a square. We can split this as minus 1 into a square, which is equals to plus or minus square root of minus 1 into square root of a square. We know that square root of minus 1 equals to I, and square root of a square equals to a square power 1 by 2, which is equals to a power 2 into 1 by 2, which is a power 1, a, right? Now we can replace square root of minus 1 by I and square root of a squared by a. So you got m equals to plus or minus ai or ia. Okay. Or you can write plus a square as minus of minus a square. We know that I square equals to minus 1. Then we can see, we'll write this minus a square as a minus 1 into a square. And we can replace minus 1 by I square. Then we'll get m square minus of I square into a square, which is equals to 0. Then m square minus, you can write I square into a square as ai whole square, right? Which is in a square minus b square equals to 0 form. So here you're having a square minus b square, right? You can write it as a plus b into a minus b, right? We can write this as a plus b into a minus b, right? Now equate each factor to 0. If you equate m plus ai to 0, okay, we'll equate two factors to 0. Then we'll get m equals to minus ai from m plus ai equals to 0, and m equals to ai from m minus ai equals to 0, right? So then m equals to minus ai and plus ai, which means that m equals to plus or minus ai. Right? We'll get the same thing. So our roots will be m equals to 0 and plus or minus ai, which means we got three roots: 0, plus ai and minus ai. When we have only one root, say m1, then the complementary solution to this will be yc equals to c1, one constant into e power that root into x, right? If we have two complex roots, or here plus or minus ai is a irrational root, or we can say it as complex conjugate. See, if a plus ib is a complex number, then the conjugate of this is a minus ib. Likewise, if we have plus ai, then the conjugate of this will be minus ai, right? If we have a minus ib a complex number, then the conjugate to this will be a plus ib. Likewise, if we have minus ai, then the conjugate of this will be plus ai, right? So if we have complex conjugate roots, say a plus or minus ib, then the complementary solution will be e power ax into some constant. Here we have already used c1, right? We have three roots. For first root I have used one constant, so here I am going to use another constant c2, say, into cos bx plus c3, another constant, into sine bx, right? But in our case, real part is 0, so we'll get e power 0x. Since e power 0x equals to e power 0, which is equals to 1, then we'll get only c2 bx plus c3 sine bx. c2 cos bx plus c3 sine bx. So now let's write complementary function. Yc equals to, first we will write for 0. c1 e power 0 into x plus, now for plus or minus ai, c2 cos, for b equals to a, you'll get bx plus c3 sine bx. sorry, here we are having A, right? You'll get A, not B. Okay. Then our YC becomes C1 e power 0x is e power 0 plus C2 cos AX plus C3 sin AX. Then YC equals to C1, since e power 0 equals to 1, then you'll get C1 plus C2 cos AX plus C3 sin AX. Now let's find YP. So yes, before writing complementary function, I forgot to write one thing. We got m equals to 0 and plus or minus ai, right? Which are roots of our auxiliary equation f of m equals to 0, right? F of m equals to 0 is nothing but m cube plus a square. I'll write it here. M cube plus a square plus m equals to 0. Okay? These are the roots for m cube plus a square plus m equals to 0, which are distinct and imaginary. You can also say distinct and one distinct root and two imaginary roots. Or one distinct and complex conjugate. Okay, fine. Now let's find particular integral. We know that particular integral is given by yp equals to 1 by f of d into q. We have f of d cube plus a square d into q is sine ax. So we have yp in 1 by f of d into sine ax or bx form, right, for a equals to a. Now, we can solve this using two ways. Okay, let's see. Firstly, we have to find d square, which is given by minus a square. Also, we have a equals to a, so we need to replace d square by minus a square in the denominator. Always the denominator must be not equals to 0. So consider d cube plus a square d, the denominator. Okay, we can write d cube as d square into d, then we'll get d square into d plus a square d. D square appears, right? So let's replace d square and see what we'll get. Minus a square into d plus a square d, which is equals to minus a square d plus a square d, which is equals to 0, right? So by replacing d square by minus a square, we'll get the denominator, which is equals to 0. Then we'll get 1 by 0, right? 1 by 0 into sine ax. By replacing d square by minus a square, we'll get 1 by 0 into sine a square. If you want, I will show you. We have 1 by d cube plus a square into d into sine ax, right? The same thing I have written here, equals to 1 by, after replacing, or better, d square into d plus a square d into sine ax will be 1 by d square is minus a square, so you'll get d square. If you replace d square by minus a square, you'll get minus a square d plus a square d into sine ax, which is equals to 1 by minus a square d, and plus a square d gets cancelled, so you get 0, right? 1 by 0 is undefined. So what we'll do, we'll not replace d square here. Okay, so we'll write 1x into 1 by, find the derivative of f of d. If f of d equals to dq plus a square d, then f dash of d will be 3d square plus a square, right? Derivative of 3d cube is 3d square plus derivative of a square d is a square. Again here d square appears in the denominator, right? Now we'll check by replacing d square by minus a square. We should get the denominator not equals to 0. Okay, denominator must be not equals to 0. Just keep that in mind. And check by replacing d square by minus a square. You'll get minus 3a square plus a square, which is equals to minus 3a square plus a square is minus 2a square. Minus 2a square is not equals to 0. So what we can do? We can just replace d square by minus a square. Then we get x into 1 by 3 into minus a square plus a square into sine ax, which is equals to x into 1 by 3 into minus a square is minus 3a square plus a square. So we'll write the same step, okay, into sine ax. This becomes, or yp equals to x into 1 by minus 3a square plus a square is minus 2a square into sine ax. You can write 1 by minus 2a square as x into minus 1 by 2a square into sine ax, which is equals to minus 1 into x is minus x by 2a square into sine ax. Okay. Therefore, yp equals to minus x by 2a square into sine ax. Now let's see another method to find yp here. So we have dq plus a square d. Both, in the denominator we have d in both the terms. Right? We have, or d appears in both the terms of denominator. We can take d common here, then we'll get d square plus a square into d, right, into sine ax. Then we can just split this as 1 by d square plus a into 1 by d into sine ax, right. Now we'll write this as 1 by d square plus a square into, firstly we'll find 1 by d sine ax. 1 by d is inverse of differential operator, right? Inverse of differential operator. So we need to find integral here, integral sine ax dx, which is equals to 1 by d square plus a square into integral sine ax dx is minus cos ax by a, right? Again, we'll split this as 1 by d square plus a square into, you can just write this as minus 1 by a into cos ax, right? So here minus 1 by a is constant. We'll write it first. Then we'll get minus 1 by a into 1 by d square plus a square into cos ax. we are having minus 1 by a into 1 by d square plus a square into cos ax. So let's find 1 by d square plus a square into cos ax first. Or you can just name this as some yp1 for your convenience. 1 by d square plus a square into cos ax. Right? Here q is in cos ax form. Right? Then we need to find d square, which is given by minus of this square, a square, because we have for a equals to a. Or you can just compare this with for q equals to cos bx. You can also say that q is in cos bx form. Then we can find d square by using minus b square. Then for b equals to a, you'll get minus a square. Okay, don't get confused. We'll just find d square, which is given by minus this number square. Okay. Now we'll check d square plus a square by replacing d square by minus a square. Consider 1 by d square plus a square into cos ax. I'm taking the whole thing. If you want, you can only check with this. Okay. Then we'll get 1 by, replace d square by minus a square, you'll get minus a square plus a square into cos ax, which is equals to 1 by minus a square plus a square is 0 into cos ax. We know that 1 by 0 is undefined. So here we can't dare to replace d square by minus a square. So what we can do? We have to write 1x into, find the derivative of this. That is, you'll get 2d. Derivative of d square is 2d plus derivative of a constant is 0. So you'll get 2d into cos ax. Right? Which is equals to x by 2 into 1 by d into cos ax. Now we can find 1 by d cos ax. Equals to x by 2 into integral cos ax dx, which is equals to x by 2 into integral cos ax dx is sine ax by a, right? Which is equals to x by 2a into sine ax, right? We got the value of yp1, which is x by 2a into sine ax. Since 1 by d square plus a square cos ax equals to this one, so let's replace yp1 by x by 2a sine ax. Then we'll get yp is equals to minus 1 by a into, replace 1 by d square plus a square into cos ax by x by 2a into sine ax, which is equals to minus 1 into x is minus x by 2a into a is 2a square into sine x. We got the same thing, right? Therefore, yp equals to minus x by 2a square into sine ax. Now we can write the general solution. The general solution is given by y equals to yc plus yp. Y equals to, we have yc c1 plus c2 cos ax plus c2 sine ax plus yp minus x by 2a square sine ax, right? which is the required solution. See here we have used same constants, just change the constant as C3, another constant, okay? Third constant as C3. Fine. Now this is the required solution. So we have seen a problem from higher order linear differential equation in this video. Hope you'll understand. We'll see you in the next video. Until then, bye bye.